So that's the deal, okay? So this is a subject that has been in my thoughts for quite some time. It started as a hobby, and as it often happens with hobbies, it became an obsession. And I guess before getting into the subject, I will give you a very quick explanation of why I ended up working on this. But this started with the paper almost 20 years ago. We were thinking and trying to understand properties of the energy momentum tensor in cosmological backgrounds, in that particular case, the null energy condition, in effective field theories. And then, across the years, I have done work, and the work I will discuss today is based on stuff that I did with this gentleman already almost 10 years ago, but which was dropped because we were all not very convinced of what we were getting. And later on, in collaboration with a master student and postdoc, we went back and we reanalyzed the issue, and we wrote a paper, and now I'm going on. There's some recent stuff going on with a bunch of people that's spreading in different directions. So my point of view, what I'm saying today, will probably be different. Hopefully be different in sometime in the future, but I'm yet in a transition. So I will present the point of view as it was a few months ago, maybe a year ago. So what's the deal? So one question you can ask is, what is cosmology? And cosmology can be described as a situation where gravity plays with a finite density system. Okay? Finite density system, in the case that we care about in cosmology, is a situation where you have a medium, and a medium homogeneous and isotropic, and that can be formally described by a situation where the symmetries of space-time, okay, microscopically, Poincare symmetry of space-time, is, in a sense, spontaneously broken to the subgroup of translations and rotations and time translations at the level of the microscopic system. Then, of course, there's interaction with gravity, and things get more involved, but that's essentially what there is. And as we are familiar with the spontaneous breaking of symmetries, that mandates the presence of soft modes, which in the quantum mechanical case we call Goldstones, in the classical case we call soft modes or hydrodynamic modes, and whose properties are largely constrained by the symmetries, okay? By symmetries and locality. So if you view cosmology this way, and if you are a model builder, like I am, the question is, what is possible at all? In what are the constraints in theories, let's say theories beyond the standard model, or crazier theories on this source of evolution, on this source of gravity? Okay. So essentially, exploring the space of possible cosmologies is, in a sense, exploring the space of possible sources of T mu nu, which is exploring the space of possible finite density systems with their dynamics. So the question is, which options for T mu nu are even possible? So what is the space of sensible EFTs realizing this breaking? I should say that questions like this were around in the early 2000s, when it became clear that the universe was accelerating, and the question is the cosmological constant the only option? And some of the people here, also Sincha and Marcus, we were all involved in trying to understand the so-called modifications of gravity. By the way, the fact that the fluid modifies gravity, or a finite density system modifies gravity, was clear to Anderson already in 1962 when he wrote a paper about the plasmon mass. Okay. Essentially said, look, when you have gauge a particle, a massless particle with non-zero helicity, a gauge field, could be a photon or a graviton, the presence of degrees of freedom that, in a sense, non-linearly realize the symmetry, like the Goldstone bosons, modifies the short distance dynamics. In the case of, he was thinking of plasmas, the plasma mode can mix with the photon and give a gap, create a gap in the photon. Well, in the case of gravity, that has a different effect and can view the Jeans stability as a similar, as a phenomenon in the same class. This was 1960, quite a remarkable paper. Anyway, so let me give you examples of so when you start, so we were studying crazy theories, and I mean, and we wanted to understand how crazy we could get. So what is the space of theories with this, of systems with this, realizing that, and what is the space of consistent theories. Let me give you the example of the simplest example of a finite density system illustrating this spontaneous symmetry breaking. That is given by the relativistic superfluid. So you can formally characterize a relativistic superfluid or a superfluid as a system that non-linearly realizes Poincaré times. By the way, at this stage, I already forgot about gravity, because gravity becomes important when you go to large distances, which is distances where the mixing between these hydrodynamic modes and the metric are important. While if you go to short distances, the aerodynamics decouples. That's, for instance, the reason why in this room the hydrodynamic modes that I emit to give this talk are not sensibly affected by gravity. The same situation happens in the electroweak theory, where if you go to very short distance, the longitudinal modes of the W, which are essentially the Goldstone boson and the Higgs multiplet, are essentially decoupled. They have their own life. I mean, they have a different, I mean, they are coupled, but they do by all means behave like the scalars in the Higgs data. That's the equivalence theory. But at time scale and distance of the order of the W mass, you have to treat them together. So I'm now zooming on flat space. Okay, there's no gravity. So a superfluid is a situation like this, where the symmetry is broken down to ISO 3, and an effective time translation that is the linear combination of the original time translation and the internal charge times a coefficient that is as the interpretation of chemical potential. And to realize in the simplest way the situation, as shown by Son in 2002, you just need to, as in all situations where you have spontaneous symmetry breaking, once you've identified the pattern of breaking, the minimal long-distance dynamics is the one that is controlled by the only degrees of freedom that are really mandated, and these are the soft modes, that is to say the Goldstone modes. So the simplest way to realize that, to construct the Goldstone fields, is to have a scalar field that shifts under this symmetry, and then consider a background where the scalar field, which has a shift symmetry, so it's derivatively coupled, has a background that grows linearly with time. This is the fluctuation. In other words, you're in a situation where the field can be viewed as a clock. Okay? Its value measures time, so rather than saying what time is it, you can ask what is the value of phi. Of course, in realistic situations, this phi is just the phase of some scalar field or some condensate. Okay? But as a matter of fact, is the only relevant degrees of freedom at low distance. And if you want to construct the dynamics, you just have to form objects that are Lorentz invariant, I mean Poincaré invariant, and translation invariant. And at the leading order in the derivative expansion, which is what you're aiming at long distance, that's the only invariant you can write down, and the action is the most general function of this x. This function is a one-to-one correspondence when you derive the adjoint tensor with the equation of state, and as a beautiful illustration of the power of symmetry in this situation where the symmetry is spontaneously broken, very much like with the pion Lagrangian, this equation of state, okay, which you can measure in static situations, also controls the soft photon scattering. Okay? because once you have this function, and then when you expand around fluctuations, the same function controls the endpoint function that controls the scattering. Of course, these are leading order in the derivative expansion. At the next order, you will have more than just the equation of state, but that's always the case when you have this situation like with the pi-Lagrangian. At the leading order in the pi-Lagrangian, everything is controlled by f pi, and when you go to the next order in derivatives, you get more. But that's still systematic. This is the simplest example, okay? And by the way, inflation, you can view inflation, or the situation where there's a scalar field, slow rolling, as essentially a deformed superfluid. Okay? In fact, in inflation, the scalar field itself plays the role of the clock, only that instead of having an exact shift symmetry, you have only an approximate. Let me get instead to what will be the subject of this talk, it is the fluid. So the fluid, in a sense, is I mean, if the superfluid is like having a clock, the superfluid, the fluid or the solid also is like having a ruler, okay? And in what sense? Well, before I had one scalar that satisfied the shift symmetry, and in this situation you can realize universally the dynamics of a solid or a fluid by thinking of three scalars with each of them with a shift symmetry, but in a background where there's a one correspondence with the value of the scalar and the space position. Okay? In other words, rather than asking where you are, you can ask what's the value of phi. Okay? And then whether you are a solid or a fluid depends on the internal symmetry of this phi field system. Okay? If the internal symmetries are just internal translations and discrete or continuous rotation, then you have a solid. The situation where you have a fluid is the one where the internal symmetry is actually extended to the full volume-preserving diff reparametrization. In other words, reparametrizing phi by any mapping that satisfies the conservation of the volume. If you impose, and intuitively, this symmetry, the fact that the symmetry is to do with the fluid is just tell you that a fluid is it's a system where if you take its parts and you turn them around and you displace them without compressing them, the energy doesn't change. That's intuitively. And therefore somehow, this is somehow how the way in which you can justify this construction. But this is just an abstract field theoretic construction. You have symmetries and symmetry breaking, and the degrees of freedom that are dictated by that. In this situation, again, you have only one invariant you can write down. That is, invariant is Poincare invariant and SDiff invariant at the leading order in the derivative expansion, and it is the determinant of this sort of meson field. Again, the Lagrangian, therefore, is a function of this determinant. It's just a function of one quantity, and again, when you derive the Angelo-Anton tensor, you realize that this function controls the equation of state of the fluid, okay, because I want to have correspondence. And you can check, and this action, its equation of motion precisely corresponds to the Euler equation of a relativistic perfect fluid. And the question that you may ask here is, what is the implication of this symmetry, okay, in terms of Born identities, by Noether theorem? And the implication is the well-known property of perfect fluid, that is Kelvin's theorem, which is, okay, I don't want to get into detail here, but it's just the fact that vorticity is conserved along the flow. This is just a relativistic version of that. Now, however, but other than that, you can view this.
You don't mean that in all dimensions. You don't mean that in all dimensions. You mean that in 2 plus 3 plus 1. What do you mean by vorticity?
Oh yeah, then it's a higher form. It can be a 3 and higher form. Yeah, it's a different form in different dimensions. But this construction is independent.
I mean, I would have said something different. I would have said that this volume preserving diffeomorphism does something that's important for the ideal fluid, namely ensures no entropy production. for an incompressible non-relativistic
This is
fluid,
compressible, eh?
yeah, this is relativistic, but incompressible. For an incompressible non-relativistic fluid,
But let me say it this way. Given that I'm writing a field theory here, it's a mechanical system.
Yeah.
It's a mechanical system for which I write an action. Entropy is not produced, even independent of the symmetries. If I have a Lagrangian system without any. So that's the entropy conservation here. It's an unavoidable fact that I'm writing an action.
yeah, it's just that you want to go beyond what you want the perfect fluid.
That's what you have done.
Yeah.
That's what I'm not able to do. But that's where we get to the, yeah. What I'm doing here, I'm taking, see, I should maybe to justify myself. We were trying, this effort here was trying to explore exotic things, okay? Of course, it makes sense to explore less exotic things, fluids that exist, okay? And this is where, in fact, where I'm going back now. But this was to explore these more exotic situations, and among the exotic situations, this seemed like a quite simple one, and then we want to understand, does it make sense? Does this field theory make sense as a quantum field theory? Is there, and that is where you encounter the knowledge thing, okay? And this is why I got obsessed. And let me tell you very quickly where this is, okay? In fact, as a consequence of the symmetry and in relation to Kelvin's theory and to the properties of perfect fluids, in consequence, that you can see right away as a bread and butter field theorist, is that when you study the system and now you expand around call it the ground state, the stationary situation, where phi is equal to x, with the small fluctuations, and you go to quadratic order, you discover, okay, now around this background, the internal indices, the phi I, become tied with the space indices, so that this fluctuation here should be viewed as transformed as a vector under the unbroken rotations. Okay, so it's a vector field. Okay, and the vector field, the modes in the vector field, you can decompose them in a listed representation. It's going to be 1 minus 1 and 0. 1 minus 1 of the transverse and 0 is the longitudinal. And these different representations don't have to have the same dispersion relation. And in fact, we find the following quadratic action. Okay, the gradient part of the action only involves the longitudinal field. Okay? While in a solid, you would have different speed of sounds for transverse and longitudinal. Let's say if it's a homogeneous isotropic solid, you get just two speeds of light, one for the transverse and one for the longitudinal. Here, you find that the speed of sound of the transverse is 0. Okay? In other words, there's no gradient energy for the transverse mode. And the longitudinal, the compressional modes, the ADCT0 mode are just ordinary sound. Now, this property, okay, that the frequency that you obtain by expanding the Lagrangian quadratically is 0 for any k is quite unique with respect to what we are familiar with in quantum field theory, because essentially this violates our normal intuitive understanding that going to short distance, meaning going to high momentum, high wave number, corresponds to going to high frequency. Here, you can go, you can be at very short distance while being at very low frequency in slow motion. And that's, in a sense, the property that you already see at this quadratic level at the basis of turbulence. Turbulence is just the fact that even if you have a very big whirl created by a big boat, then this can evolve by branching and creating smaller and smaller motions that also have small frequency. Okay, so and until the energy of the motion is dissipated in a realistic fluid at some shorter distance. In other words, you are probing short distance in the form of heat by starting with very soft, long motion. In a sense, it's like as if you're building a Planckian collider. You're going to short distance, although things are not as nice as that. Okay, So in other words, but technically, from the point of view of would be attempt to treat this as a quantum field theory, the issue here is that the transverse phonons, which you would have thought they behave at long distances weakly coupled degrees of freedom because their Lagrangian is derivatively coupled, do not form a Fock space because they're not a set of harmonic oscillators. Technically, that means that the vacuum, okay, is not localized in field space. Okay? When you have a harmonic oscillator, the vacuum is localized close to the origin in Q. When the frequency goes to 0, the thing is totally delocalized. In fact, for a free particle on the line, which is the limit of a harmonic oscillator when the frequency goes to 0, you don't even have a ground state. The wave function is completely spread. Of course, if instead of a line you have a circle, you have a wave function completely spread on the circle. And here, in a sense, it's like having a very complicated circle because the system spreads around, but goes around, comes back. Okay, the motion inside. I mean, okay, I'll make this very clear. Okay. So then, in any case, you cannot treat this system perturbative like in ordinary weakly coupled quantum field theory. So the question is there any way, does this system make sense as a quantum theory? Okay? So this is a situation where the symmetries are forcing on you with something that you have never encountered before, and something where it seems like the UV is more important than in ordinary effective field theory. It seems like this is not, it's not a very effective field theory. But the question is, can be effective in a different way, and this is the reason why I got interested.
But doesn't this just tell you that you really need to keep the next order terms?
This is true too. This is fixed also by, I mean, the next order terms don't change things. Okay? Things change if you go around a non-trivial configuration where things move.
I mean, you could imagine doing two things, which is related to the last question. In a physical fluid, that those modes that you're talking about would actually have a dispersion at order k squared. Because there would be
an IK square.
There will be a shear mode, there will be dissipation.
A shear mode if I am considering a system where there is dissipation. Yeah, I'm treating this as a mechanical system. Yeah.
But there's another thing you can do, which is to not turn on dissipation, but look at sort of what you might want to call as a subset of non-dissipated fluids, and then you will have higher derivative corrections. Yeah,
the case where you have higher derivative corrections, let me tell you, let me see if you agree. You can think of a situation where instead of having the full volume Bosonian symmetry, you have a subgroup of it. For instance, you have only SL3. Okay. In that case, at the leading order in the derivative expansion, you get this same Lagrangian. It's an accidental symmetry, you get that, and then at the higher derivative level, you get this. Is this what you have in mind?
Actually, I have in mind getting rid of the entire volume to the that I think is an artifact of the perturbation. I can explain.
Yeah, I agree with you, but I'm just, so this is you see, if you have in mind a specific system, then you can do that. I want to study this system. No, yeah. That's, if you want, that's more like a model building question. At the end, it's a QFT question. Yeah. Okay, let me put it this way. Do I learn something in QFT? Do I get some moral in trying to study this silly system? That's, if you want, is my last line of defense.
No, that's
okay. But I completely agree with you that for relevant situations, you can.
And also, I mean, you motivated this by cosmology, but now you're restricting yourself to some small region that you don't care whether it's formulatable on curves.
No, I so cosmology, okay, so what happens, when you have gravity coupling to a fluid, okay, at long distance, that is a distance of order of g Newton times rho, the density, which is the curvature length or the Jeans mass scale, then the two systems really cannot be disentangled from one another, and then you have the interesting cosmology. But to understand what microphysics is possible at all, then I can go to short distances. At short distances, sound waves and gravity are decoupled. Okay, that's the decoupled short distance. And That's it. Then I only study I don't know whether this was your question.
That's not, okay, so I'm
Sorry.
happy to ignore the back reaction.
Because we are sure.
Because but if you wanted to have it as a sensible quantum field theory, is it a question about, is it a sensible quantum field theory on any curved space, Lorentzian curved space-time, or is it only formulatable on the Minkowski space?
My expectation is that if it is well defined as a microscopic system, then I will be able to put it on any space-time. Very much like for the standard model. The same question you can ask, does the standard model make sense in any space-time? It's a similar thing.
Then it's interesting to ask, what is the space-time description of the zero frequency, this transverse zero frequency thing? What locus?
Oh, what are these things?
What is it?
No, but the zero frequency, you know what they are, right? They're just the vortices, the smooth vortices that you have in a fluid.
But are they spatially compact or not?
You can make them as you wish, depending on the, as you know, if there is a hurricane in the Pacific and you're farther away, you're safe. In the sense that these vortex motions can be localized. It just depends on the pressure profile. Yes.
Okay, so
They don't have to be extended everywhere. They can be localized.
you're saying that the zero frequency is not interfering with
This zero frequency
global
is at leading order in the expansion. When you go non-linearly, you have a frequency that depends.
Okay, good.
Okay. But if you want to see whether you can treat this fluctuation as quanta, okay, then this is a different situation. Okay, so how do I, and one question you could have asked is, maybe this whole construction doesn't make any sense. Maybe you get quickly to a sort of inconsistency with, I don't know what it is, maybe it's a theory with a zero, that as an effective theory really doesn't make any sense, that the cutoff is zero, so you cannot really make sense of it, and that's an option. And that perhaps explains why ordinary fluid has universality classes at zero temperature that are not encountered. At zero temperature you find solids, superfluids, other exotic things, but you don't find ordinary fluids. Fluids, you find them everywhere, but at zero temperature you don't. Which means that it looks like as ordinary QFTs at zero temperature do not seem to exist. There's always some sort of classical aspect to that. So, in order to zoom on this problem, okay, given that the problem is associated with the transverse mode, I just get rid of the compressional modes. I go to the limit where the velocity of the flow is low enough that I don't make any sound. In other words, I don't emit sound waves. And that's the limit where the fluid behaves incompressible. One technical way to do that is to put the fluid on a compact space. I will put it in a torus soon, okay? And then the compressional modes have a KK tower, okay? And below the frequency of the lowest mode, then basically you never emit that, okay? So in this situation, let's say I'm working on a compact space, and there is a one-to-one mapping between the physical space and the phi space, okay? And they are essentially the same space, and this modulo situation that I go outside the theory, namely where I have cusps and stuff like that, this is a one-to-one mapping, and the incompressible limit, it's one-to-one and back. The incompressible limit corresponds to a situation where you can choose coordinates such that it's just a mapping with determinant one. So it's essentially it's a mapping. At the end of the day, it's a mapping from a manifold onto itself with respect to the volume. And this limit, okay, it's a limit necessarily of a small velocity, therefore it's a non-relativistic limit. In this limit, the action reduces to simply density times velocity, where velocity is just a derivative. Now we can invert, rather than writing phi as a function of x, we work with x as a function of phi. And you can think of phi as the label of the pieces of fluid, okay? And the velocity of that piece of fluid is simply the derivative of x with phi fixed, okay? Of course, this variable x is not a free variable, it's a constrained variable by this, okay? So this action with rho v squared is not a completely trivial action because this v is the velocity of a constrained variable. And if you want to study the derived Hamiltonian of this system, you can go through the usual song and dance of Dirac constraint Hamiltonian systems. In fact, there is a clever way even to bypass that. I hate using this methodology. I'm not very technical. Anyway, there's a way to bypass it. But that doesn't matter. What really matters, okay, here is the following. Whatever you will do, okay, when you go to the Hamiltonian, the rho, very much like when you have mv square, will end up, when you derive your canonical momentum, written in terms of the canonical momentum, the Hamiltonian will have rho in the denominator. Okay, it's very much like when you have the Hamiltonian of a particle of mass m, it's p squared over m. So rho is like m. And now you can aid yourself with dimensional analysis to guess what the gap, what the energy levels would be in this system as a function of the frequency. And so, let's say, imagine we are in n dimension and spatial dimensions, okay? Spatial, so we are in a space-time of n plus 1, okay? This rho will have a certain dimensionality, and that fixes what dimension you must have here. And there are broadly two situations, and everything in the between. There are two limiting situations which you can think of. The first is that the dynamics, okay, the gap of a mode of momentum k is completely fixed by physics, completely controlled by physics at the cutoff. Okay? These are all effective theories. They must have a cutoff, which you think in the fluid has a cutoff because there's intuitively a length below which it's no longer a fluid. You see its elements. But in any case, even without knowing what a fluid is, even if I'd never seen a fluid, this is an effective theory with a derivative expansion at best, so there will be a cutoff. And so the most extreme thing that you can have is that all the dimensions here are saturated by the cutoff. And you have something like this, where lambda is the inverse cutoff length. Okay? And this is the guess that was made by Landau in his famous 1941 paper, where he derived the theory of superconductivity. What Landau did was to start precisely, although in a different language, he precisely started with the system I'm considering here. It was as much a crackpot as I am. He started with this system, okay? So he wrote the equation of hydrodynamics and then interpreted them as operator. And then he had to face the fate of these transverse modes. And Landau argued like this. Of course, in the back of his head, he knew what Kapitsa was observing in the experiments of superfluid. So he knew that there were no transverse mode, there were only the compressible mode in the superfluid. So then he said, well, these variables, these transverse variables, satisfy non-commutative algebra. When there is non-commutativity, like the angular momentum, there is a gap. And therefore, this is the thing, you get rid of them, they're gone, and just focus on the remaining soft degrees of freedom, which is the transverse, which is the compressional mode. Which is precisely the main property of superfluids, that you don't have ungapped vorticus motions. All the vortice superfluids are gapped objects. In the superfluid, there's no such a thing as a smooth hurricane, like you have in the Gulf of Mexico. There's always a singularity in the middle, while in the fluid, you can have a very smooth situation. Oh, the extreme case, you could imagine that actually, no, what you have here is completely saturated by infrared physics, okay? And if you have an excitation of wavelength k, and here you will get k to the okay? Again, this would be interesting because they tell you that, well, these modes are actually gapped, okay? And the connection between short distance and higher frequency remains, although in a weird form. And this is what we were guessing as an option in the first paper I wrote with Nicolis and Enlich and Wang in 2010. Turns out that none of these two I think is correct, okay? And the right thing is in the middle, okay? And in order to show you that, okay, I think I have to go quickly, right?
No, you've got 27 minutes to 12.
Okay.
Sorry,
so
22.
to go very quickly, I'll focus on the simplest situation where there is something interesting to say. The lowest number of dimensions of the transverse modes, which is 2 spatial. The simplest manifold that I can treat, compact, torus, okay? So the situation is an incompressible fluid on the 2 torus, okay? And the configuration of the motion are simply are simply motions where this thing moves around without being compressed. So each of its parts, as time evolves, get remapped, preserving the volume, okay, without being compressed. So essentially, the configuration space of the system is precisely the group of volume preserving diff. To find what the configuration is at any time, you simply have to give me the mapping, the volume preserving mapping that brings the points as they start at the beginning to the final. So this is, in a sense, you can view it as a point particle moving on a group manifold. Never mind that the group manifold is infinite, but that's what it is. In that respect, this is very similar to the rigid body. Okay? The rigid body is also motion on the group manifold, and in that case, the group manifold is O3. Okay? Let's say the rigid body is like a potato. You define its position by taking 3 toothpicks and inserting them in the potato, and then the configuration of the potato with respect to the axis of the experimentalist are simply an SO3 rotation. Okay? And in fact, this correlation, and that also is a motion. The motion of the rigid body is motion on the group manifold. And this connection, this familiarity, in a sense, analogy between the incompressible fluid and the rigid body has been pointed out a long time ago by Arnold, and there is a section in his book of mechanics where he discusses this detail. Okay? And in fact, the analogy goes through nicely, and again, let me be slightly more formal. In the case of the rigid body, okay, as I said, never mind that this is SO3. Now you can really think of a rigid body for an arbitrary group. Okay, but SO3 is the one that is relevant for rotating potatoes. Okay, the configuration is given by a O3 matrix, and you can think of acting with the group both on the left and on the right. The action on the left is the rotations of the frame of the experimentalist, and that's the genuine rotations. While rotation on the right, it just corresponds to you choosing different way of putting the toothpicks on the potato. If the potato is a very ugly potato, these different choices are all equivalent. So this is not a symmetry. But you can think about acting nonetheless on the right. In fact, in the fluid you have a similar situation. If this is your configuration, I mean, it's a mapping between phi and x, you can act with the volume preserving diff either on phi, which is to say, and they call this on the left, even though it looks on the right. Mathematicians actually use, they say the only difference between solids and fluids is that left and right are exchanged. Here, I want to use left for the ones that are really symmetry and right for the ones that are broken. So the action on phi is a symmetry, the action on x is just volume preserving diff on space-time coordinate, but that is not a symmetry, so you act this way. So again, you have the same doubling. And the existence of these two symmetries is actually interesting, relevant for the discussion of the dynamics. As you're familiar from mechanics, the Hamiltonian of a rotating body, of a rigid body, is neatly written not in terms of the angular momentum projected on the axis of the experimentalist, but in terms of the angular momentum projected on the axis of the body. But the angular momentum projected on the axis of the body is precisely, up to a sign, the generators of this other right symmetry that is broken. Okay? And this, so I call R the generators of the symmetry where you rotate, where you change the orientation of the toothpicks. Okay? Turns out that, okay, so a rotating body is nothing but a 0 + 1 sigma model, very much like we do for Goldstone bosons, when we construct composite X models or time Lagrangian. The relevant objects are the angular velocities that are the elements of the Cartan form, anyway, never mind. And the Hamiltonian is quadratic, the Lagrangian is quadratic in these velocities, and the Hamiltonian is therefore quadratic in the generators of the right rotations. Okay? And the coefficient, which is the analog of the decay constant of these coefficients are the analog of f pi for the sigma model, are nothing but the moment of inertia tensor features. So now you see that for a generic potato, this is just a generic symmetric matrix, and this object satisfies the algebra of SO3, and time evolution clearly given that there is no SO3 in this Hamiltonian, makes this R evolve. So these R are not conserved. But they evolve in a very specific way that is controlled by the angular velocity. So then to find the energy levels and construct the Hilbert space, well, you know that the Hilbert space will reduce to a direct sum of irreducible representations of angular momentum. Okay? Turns out, to do that, you have to find a complete basis of wave functions on the group manifold. That is established by well-known mathematical theorem, Peter-Weyl theorem, and that tells you that the Hilbert space is a direct sum of blocks, and each block consists of a representation LL, representation L of the left group action and L of the right group action. The reason for this doubling is that you can always act with rotation in two ways. You can act in rotation by rotating the experimentalist, or rotating the body, the whole body with respect to the experimentalist. These are ordinary rotation. And that's a symmetry. And there are, yeah, you have to realize that. But you can always also rotate the toothpicks in the potato in the very same way, and this is the right rotation. And each block involves dots. So for every total angular momentum L, you have 12 plus 1 square states. Okay? And you can compute. And computing the energy level is just as hard as diagonalizing in this block. These R in each block are 12 plus 1 times 12 plus 1 matrices, and just have to diagonalize them. And the same thing goes through formally for the rigid body. The role of these right charges is played here by vorticity. Okay? The Hamiltonian is written nicely. I mean, it was V squared, but you can write it conveniently in terms of the vorticity, which is these right charges. And the role of the inverse inertia, of the inertia tension is essentially played by the Laplacian. Okay? And then the dynamics, okay, these are now satisfy the algebra of volume preserving diffs on the torus. Okay? And so for each R of x is a generator of I mean, you have, this is an infinite group, right? So the generators are labeled by the position. Okay? It's convenient for practical purposes to go to different bases of generators, that is to say the Fourier basis. Okay? The Fourier basis on the torus is just, you have generators now labeled by a couple of integers, which is just the wave numbers on the torus. And the algebra takes this form. Okay? So this is the algebra of volume preserving diffs on the torus. Okay? Sort of graded algebra. Okay? And now you have to go through, and it seems like you have to do the same thing. Find representations of this algebra, blah, 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 and find the levels. Okay? Now, of course, this is an infinite algebra. As far as I can tell, this is not a solved problem. Okay?
So it has two subalgebras which are Virasoro, weak algebras. It has two weak algebras or subalgebras because it has defense one
You're asking me whether there is a Virasoro? Probably it does.
Non-centrally extended Virasoro.
Non-centrally extended, yes. I mean, there should be some boundary between them.
I think
Probably you could put it on the sphere, but you can send this thing that needs a certain extension. But actually, I'm interested in the limit where at the end I will send the volume to infinity, so this is just boundary. Now, what really worries me, and I don't have time to really tell you, is that here too you have this doubling. You will expect to have this doubling. And essentially here, you see, this multiplicity of states here has to do to the fact that you can rotate your potato with respect to the experimenter, okay, without changing its property of motion. So all these rotations here give you equivalent configuration. You're just looking at the potato like this, but the orientation of angular momentum with respect to the potato is the same. This is actually, when you actually act with rotation here, you're really changing the orientation of angular momentum with respect to the potato. And this will now be a different inequivalent motion. Now here, again, you have this doubling, and this, the one that is really symmetry corresponds with given a certain configuration and relabeling the internal variable phis. But these variable phis are not the ones that we observe in the fluid. In the fluid, we only observe the velocity. And this corresponds precisely to acting here. So in other words, in this construction, there is essentially a doubling of the entropy because the number of states goes like the square, okay, which has to do with variables which we normally don't observe. And this is a bit worrisome. So how to go around this? One possibility is to gauge this symmetry. I say, look, I don't want to have this multiplicity, I gauge it. But if I gauge this symmetry, I'm forced to project my Hilbert space on the states that are invariant under this symmetry, which is to say, well, is the trivial representation here. But if the representation is trivial here, it's trivial here as well, and the velocity is 0. So if I do this gauging, this is precisely what Landau should have done. Because when you do this projection, then you completely project out the transverse mode, and you're back to the superfluid. And this is in a sense what the basis of Feynman criticism of Landau's approach. Okay? Although Feynman was a clever guy, he didn't present it in this sophisticated, silly way I'm doing now. I'm not just telling you that this is clever, but it's just, for him it was obvious because of issues with indistinguishability of particles. So, okay, if I do that, then it's the end of the seminar, okay, and there's basically no fluid at that point, okay? But there is something here, that would have been throwing away completely the transverse mode, and this all goes to 0, okay? So there's only compression. Instead, I want to see how far I can go keeping this, okay? And what I can do is to go on and pretend not to worry about this mysterious additional multiplicity, or if you want, I can proceed by working with this Hamiltonian and finding a representation of this algebra. Now, how many times a given multiplet under this algebra will appear in the Hilbert space, it's something I cannot control. Here I could control it because the Hilbert space is fixed by the complete set of wave functions of the group manifold. If I give up this other thing, then I cannot tell you how many times the representation appears. But I can see what happens if there's something interesting going on.
Do I understand right that if so, gauging would you say that gauging is the only way to get the right physical degrees of freedom, and so now you're considering some theory that has
is the only way to get the number of seems the only way to get rid of this puzzle of the multiplicity. Now, maybe there is something I'm missing about this. Maybe I have to live with this puzzle.
As you said, these phi's are not directly observable.
I would say so.
So if you keep everything, it seems that you're considering some theory. It may be a sensible theory, but you wouldn't call it the quantization of this theory because it has additional degrees of freedom that you
No, it is the quantization of this theory. It is this theory. It's only that because in this theory the phi's were degrees of freedom. Okay, it's just that it doesn't seem intuitively to conform to our notion of a fluid. Okay.
So you can just think of it as a theory on its own.
Yeah, it's a theory. It's on its own. Okay, Marcus. Yes,
right.
yes. Now, how do I proceed to do that? Well, okay, working with this infinite group is complicated, but it turns out that the volume semi group on the torus can be viewed as the limit for n goes to infinity or SUN. Now, SUN, this is something that was pointed out long ago in the context of membrane theory. Some sort of that is also, this was also realized in the context of condensed matter system. In particular, Wigman is one of the people who is mostly trying to get results out of that. There's even a paper by some statistical physicists that try to understand ordinary classical fluid in statistical mechanics using this, and their goal was to understand the red spot on Jupiter. So just there is a variety. There is a wagon of people of colorful people driving. I am the last of this group of colorful people. Okay. Anyway, so you see, but viewed this way, now is becoming a rigid body problem. Once you buy this is just, instead of the SO3 rigid body, is the SUN rigid body. It's the potato whose axes are along the generators of SUN. Now, and to work things out and to see how this relation between the volume preserving diff and SUN works, one can use a clever parameterization of the algebra SUN, which was invented by Toft in this paper on monopoles, as you remember. And you can do the following. Let's take an n that is odd. In fact, I want to take an n which is the square of an odd number, okay, eventually. But let's take n odd, and then you can label the entries, the indices of the fundamental from minus to plus, okay? Minus n over 2 plus n over 2. And now a matrix, an n by a matrix, which is essentially the adjoint, will be characterized by two integers in this range. These essentially are the position of the square and rows, I mean, of n by n matrix. And you see, this is a couple of two integers, which looks like the labels, start looking like the labels of the generators of the volume preserving diff group in Fourier space. Okay? And there is n square of them. Now, you can construct a basis of the generators of SUN, which is in one-to-one correspondence with this couple of integers, excluding the 0, 0, okay? After all, the number of generators is n squared minus 1, so n squared here minus this is n squared minus 1. And these generators, which I'll tell you in a moment how they construct, in this basis, the SUN algebra takes this form. Okay? So it looks like a graded algebra. Okay? Of course, there is a periodicity. These j, n plus m have some periodicity, okay? Because there's a finite number of them, and with this coefficient. And, well, the way this is constructed is by considering these two. This is all Toft, okay? Take these two matrices. These are roots of the identity, of the unity, okay? And the Jn are simply given by this, okay? So, simple algebra problem. Now, what's the deal with this? Well, if I consider the generators of SUN that I wrote before in that basis, and I rescale them by this factor, then the algebra takes this form. And if you look at it, it starts taking the form of the volume preserving diffs. In particular, well, more precisely, if this, call it momenta labels, are small enough, that is to say smaller than square root of n, okay, then you can expand the sign, you can approximate the sign by its argument, and this becomes precisely the algebra of volume preserving diffs. Okay? So let me say that, all to say is that SUN has n squared generators, and within this set of n squared generators, there is a set of n generators, okay? Because you have to take a small subset where these n's, I mean, this n field is n square, okay? If you take those where these labels are small, okay, and there is essentially n of them, they're algebra approximate. So there is, I'm introducing this huge set of generators, and it's like gold mining, okay? And the ones I care about are really a small subset. But when n goes to infinity, this subset also goes to infinity. Okay? So in a sense, this had to be in a sense, because I wanted to, I needed a way to UV complete. So in a sense, this embedding of the volume preserving diff group into SUN is a way to UV complete. I mean, I still have a symmetry, okay? Instead of volume preserving diff, I have SUN. So it's a deformed, right? It's a deformed symmetry, but still I have all the features. So the fact that now these label n are finite, and they live in this square, while in the torus these go to minus infinity plus infinity. Just the fact that momentum is now finite means that the space is latticized, okay? And to go to position space, you simply have to do a discrete, I mean, finite Fourier transform between n and x, okay? And the way to do that, it's a standard thing, like it's a discrete Fourier transform where the Fourier modes are simply the roots, the squares, I mean, powers of the roots of the identity. How much time do I have?
I was going to ask you the same question. How much time do you need? I mean,
I can do it in 5 to 10 minutes.
Yeah.
Okay. So let me go for to try to shorten a long story. As I said, I have this rigid body in SUN but only part of the generators are the ones I want to care about. And these are the generators corresponding to small wave numbers, small enough. Okay? A small wave number corresponds to large space separations. Okay? Okay? And in this particular case, it implies that I have to consider points in this discrete torus that are separated by more than the square root of n. So as I said, my torus is an n by n torus. Okay, but I can view an n by n torus as a square root of n by square root of n torus, say coarse torus, where in each of the boxes there are square root of n by square root of n smaller boxes. Okay, and now the coarse lattice is the lattice, this lattice squares that contain many more points are on a length scale where I expect where the algebra of the corresponding generators coincides, of SUN coincides with that of the SDiff. In other words, the effective theory of the fluid should only be valid on length scales that are large compared to the size of the coarse lattice. Okay? And this coarse lattice, which is okay, if the total length is the length of the torus 2 pi r, the size of the coarse lattice length is that divided by square root of n. Okay? This length here is what defines my cutoff. Okay? While the individual guys here are 2 pi over n, 2 pi r over n, the coarse lattice is 2 pi over square root of n. And this quantity, this length here, the inverse of this length, is supposed to be my cutoff. And again, you remember the Hamiltonian was the sum of the charges divided by the Laplacian. In Fourier space it's just this. But if I do that for the SUN rigid body, I have to remind myself that I have to be conscious of the fact that only for small enough n, this is really fluid. So I have to cut off this sum. And I cut it off in, I mean, there's going to be some dependence on the cutoff, but I cut it off. It's like a choice. It's like choosing a rigid body with a specific moment of inertia. Okay? But in the far infrared, this Hamiltonian coincides with the one with the fluid. Okay? So I expect that this describes the fluid. Notice that if I rescale everything, there's an overall coefficient, which is precisely the gap of Landau. So it looks like I'm on Landau's side. However, things are less obvious. So let's study the spectrum. Now, studying the spectrum is simply amounts to taking these J's in representation of SUN and computing this Hamiltonian, the energy levels of this Hamiltonian. So if you start with the trivial representation, that's easy, the energy is 0. If you go to the next, you take the fundamental representation, okay? And what you find is that the energy of all the states in the fundamental representation is the same, and is given by this overall gap coefficient. However, with the contribution that diverges logarithmically when the size of the torus goes to infinity. And when you introduce a single thing and you have a log in 2 dimensions, that speaks for a vortex, okay? Okay, and let me tell you better. And in fact, how many of these states you have? Well, you have n, and how many sides do you have on the coarse lattice? You have n. And in fact, you can really construct wave functions for these states that correspond to something happening only at the sides. And what is that something happening at the side? Is just a vorticity. Okay? So you can construct a basis of states. It's a nice thing to do on this lattice. This is pure group theory, but it has an interpretation in terms of this torus space. So these states essentially have vorticity that is localized where you put at the corresponding point. And then there is a background, because the total vorticity integrated of the torus is 0, so then the total integral has to be 0, so there is a smooth background, okay, of opposite value, okay, such that the average is 0. But when you send the volume to infinity, this drops and you just have a vortex. And what about the anti-fundamental? Well, the anti-fundamental is n minus 1 fundamentals anti-symmetrized. The fact that there is, given that each fundamental is putting a vortex somewhere on the coarse lattice, having n minus 1 of them anti-symmetrized means that they have to put a vortex at each of n minus 1 points. Okay, so they are all at different points, but I only have n minus 1, which means that there is a spot where I didn't put anything. And now, if you draw the flow of this is equivalent to having something flowing in the opposite direction there. So The anti-fundamental is just an anti-vortex placed at that point. Okay. And now this, you can view the picture for the vorticity, for the velocity in the states. Okay. It's just a vortex. This is truly, and this looks like a vortex of a superfluid because it's gapped. Okay. And you can go on and study the spectrum, studying higher representations. Okay. This. You find that they're all gapped. Okay. Until you get the representation to the first representation that realizes the center group Zn trivially, that is to say they're joined. And here things go differently. Okay, why? Okay, well, you can view their joint as the tensor product of a fundamental and anti-fundamental. In this tensor product, which is dimension n squared, there is the joint plus a singlet. What is the singlet? Well, the singlet corresponds to placing a vortex and anti-vortex on top of each other, and then having an entangled state where they're all placed at different points. Okay, so this state is a singlet. Okay, and I already computed the energy of the singlet. It's 0. Okay, but now imagine that instead of summing all these vortex on top of an anti-vortex with coefficient 1, I sum them with a modulation which is very smooth. Well, this state locally looks like a singlet, which means that when this smoothness approaches 1, its property must approach that of the singlet state. In other words, the energy can go and be arbitrarily small. And in fact, this is precisely what happens. You find that modes where the two vortices are basically on top of one another are not gapped. Okay? And essentially, you have two situations here. When the two vortices are very close in their joint, the energy is small, and when they're separated, it grows logarithmically. Okay? So, essentially, you have a spectrum of this type. When the momentum is less than this fundamental cutoff that was forced on me precisely by the fact that SUN is not precisely the volume of SDiff, you get this. And what is this? This looks like the kinetic energy of a particle that is made of matter that is over a distance, is like a volume of fluid on the size of the cutoff moving with momentum. Okay. And how to interpret this states? Well, if you look at them properly, you find that these states you can choose a basis of these ungapped states, which are essentially dipoles of vorticity. They're like a vortex and anti-vortex nearby, and one moves the other. Okay, and the more they overlap, the less they move, the less velocity they have. Okay, and their momentum is proportional to the dipole of vorticity. Okay, so there is something. Okay, there is some objects. By the way, why don't you have these in superfluids? Well, this corresponds to two vortex anti-vortex overlap to one another at a distance that is less than the distance of the cutoff. So the fact that this thing exists, I mean, it's not in the superfluid. This doesn't happen. Okay, these guys annihilate, and that's it. Here, basically by construction, they don't.
Are you saying that somehow this is a light mode, but it's an artifact of your UV regulator?
No, it's a light mode that exists because of my construction. It's the fact that my construction is not a superfluid. Makes sense. A superfluid would be a situation where I only have fundamental and anti-fundamentals. And here
what is keeping them from annihilating?
I mean, these guys, I mean, here they are in their joint, right? They are this particular representation, and the evolution remains in their joint. It's just by construction. Perhaps this analogy with the superfluid is a bit misleading, but it cannot do anything else than this. In fact, if you have, then you can also, okay, this is just for a single, and so we call these things vortons, okay? Now, you can ask yourself what happens when you have more than one. Having more than one corresponds to having tensor products of adjoints. Okay, tensor products of adjoints can be combined either symmetric and antisymmetric. And if you keep only those representations that remain, do not form a set of measures 0 when you send the volume to infinity, you have essentially two sectors of two particle states, a bosonic sector and a fermionic sector. Okay, and to cut a long story short, the time evolution in each of these sectors turns out is, and even the presence of the states is described by an effective Lagrangian of this type. So this Lagrangian is very much related to what I had before, where now I'm realizing the R charges, these generators, the volume preserving diff, by this bilinear in some Fock type creation destruction operators in position. These are like local fields satisfying standard commutation relations. Okay, they can either be bosons or fermions. Okay, and this actually reproduces precisely all the physics. In particular, it looks like at first order that there is no gap, right? In the Hamiltonian, this is gone, and you only have a quartic path. But when you normal order this generates precisely the k-square dispersion relation I had before. Okay? And now you can compute scattering amplitudes. By the way, you may ask yourself, could I have started here directly? And actually, there is another formulation of fluids, which is the one in terms of Clebsch variables, where I would get directly here. Okay, so anyway, this, you see, this Lagrangian depends. It's just based on symmetries. The only free parameter is rho. So the scattering amplitude you get here, well, there is hiddenly the UV cutoff, but the only free parameter you have in the action is rho. It's almost like, it's very similar to the pion Lagrangian, and it makes very strict predictions on the properties of these objects. In particular, if you consider the scattering amplitude in the bosonic channel, you get this, okay, where P and Q are, where P is the total initial momentum and Q is the difference of the two momenta. Okay? So this in particular tells you that if these two initial momenta come at 90 degrees, okay, that corresponds to a situation where this is orthogonal to that, which is when P squared is equal to Q squared, and this is 0. So there are particular quanta that when they scatter at 90 degrees, they go straight. Scattering only depends, it's controlled by the deviation from orthogonality. So this is the ideal crossing intersection in New York. Okay? Avenues and street go straight. In the case of fermionic, you have slightly more involved, but you have similar zeros there as well. Okay? Particular, when they scatter like this, the outgoing can never be parallel, even though momentum and energy conservation satisfy that.
Sorry, can you explain here? It has a quartic interaction with Lagrangian.
Yes.
Here you write it like the evolutional.
There are two ways of contracting things. It's just the contractions, okay?
Yeah, it's a contraction.
It's the contractions. Yeah. It's just the contraction. Yeah, you see, they're just because this length here is this Laplacian. Right. This thing is just the Laplacian. That's it. Okay. So the 2D quantum fluid, I arrived at a construction where I describe something that putatively is the dynamics of a 2D incompressible quantum fluid, and this dynamics somehow is encapsulated by the dynamics of the SUN rigid body with angle to infinity. Quantum flows are characterized by SUN irreps. And what about the classical limit? Well, the classical limit should be the situation where I have very large number of vortons, okay, and the field motion that they generate, because they're like dipoles of vorticity, okay, and they can compute the vorticity they generate, therefore they can compute the velocity they create. And when I have a single vortons, the velocity field they create is smaller than their peculiar velocity. So what would be the classical limit? The classical limit is a situation where you have so many of these vortons that their vorticity field overlap, and the corresponding velocity becomes larger than the peculiar quantum velocity of the objects. Okay, so that would be the classical limit. Okay, in that limit, this behaves like a classical fluid. Okay, but at small occupancy, this is a different thing. Very much like all quantum systems, when you take the hydrogen atom in the classical limit, things fall into the center. But if you look closely, you find, well, they not really fall into the center. There's a ground state there. So this object here putatively represent the behavior of a quantum fluid close to its ground state. The question is, does this thing exist? And I don't have an answer yet to this question, but I'm trying to. Thank you. Thank you for your patience.
Any more questions?
I hope I didn't go too much over time.
No, I think it's good.
So a question about your accounting. I mean, if you had a 2D instead of square lattice, so if you wanted to pack as many vortices as you can, and hexagonal lattice would have packed more. So your n squared. Sort of
But this square lattice comes
square one.
automatically by the fact that I'm working with me. It's forced for me, I didn't choose it.
But how does the fluid know? Like,
I mean, as I said, I just worked out the algebra. The fluid brings me there. I tried previously to define the fluid on the lattice, really to get a physical lattice, and then I was not respecting the symmetry. How does the fluid know?
like if you were
But
imparting in more and more.
by the way, I should say, the regime where this object behaves like a fluid is the regime where you don't see the lattice. And is the regime where the properties of the lattice are. There's one way in which the lattice matters, is that if I write only this effective Lagrangian here, when I do normal ordering, I get a divergent contribution, which I don't know how to compute. So the presence of the lattice gives me a complete UV, it gives me a UV complete theory where I can compute that. Notice something interesting, if you consider the scattering amplitudes, which is quite important. If you consider the scattering amplitudes, and now you compute the scattering phases, this is an amplitude. An amplitude is not yet the phase. You have to normalize things properly. The scattering phase is nothing but the momentum, goes like the momentum over the cutoff lambda square. Rho disappears. So in a sense, rho controls the dispersion relation, and is a way of writing the amplitude. But the scattering phase, which is the parameter or the physical quantity that controls the strength of the interaction, does not depend on rho. It's just p squared over the cutoff square. And when p reaches over the cutoff, this is a strongly coupled theory. So in a sense, my UV completion goes across the strongly coupled regime. Now, if I didn't have this UV completion, given that the theory is strongly coupled at the cutoff, I wouldn't know how to justify in detail that. So in that sense, this is not a very effective theory. In order to exist, so if I don't take into account these cutoff effects, then I don't have asymptotic states because the states don't propagate. Okay, and also if I set this cutoff smaller, I mean, and the cutoff, however, controls precisely the strong interaction scale. There's no way to deform this theory in such a way that the cutoff is weakly coupled. It's always strongly coupled. I mean, in the standard model, there's a gauge coupling G. The maximal cutoff is 4 pi V Fermi, but at the W mass, everything is weakly coupled. Here I cannot do that. I don't have the right to do that. So it's a very rigid theory, and yeah, I find it very peculiar.
Any other, yeah?
Good. Quick question. So in the next slide where you have the amplitude, does that go to 0 at some angle?
Yes, it has vanishing, it has zeros. Yeah.
Is
It has both in and both out, it has zeros. Yes.
Is there some interpretation of why that happens?
The interpretation is that this interpretation, I'm not entirely sure I have a clean interpretation, but the way I understand is because these guys are dipoles of vorticity. In fact, this interaction here, it's precisely the same as the Coulomb interaction between dipoles in electrostatics. So they are dipole, and this dipole depends on momentum, okay? And therefore, when they come at certain angles, the dipoles are oriented depending on the momentum, and the interaction can vanish. That's essentially the reason. Of course, it's more complicated than that, but that's the origin. The origin is that the interaction is a dipole-dipole interaction, and the dipole is orthogonal to the momentum. So that's essentially the reason. And that's, in the bosonic channel, this gives you intuitively why they go straight. But in the fermionic channel, it doesn't work, so it's slightly more important. Yeah, I have a candidate for this theory, for this system, if you take 2 plus 1 QED, and 2 plus 1 QED in a magnetic field, okay, in a magnetic field, and take E plus E minus, particle and antiparticle, charged particle and antiparticles. They form bound states like hydrogen atoms. Even they are also localized by Landau. They form Landau levels. But now consider particle antiparticle. They form an hydrogen atom. Okay, in the limit in which how can I say? There is a certain limit where the ground state localization is less than the localization of the lowest Landau level. Okay, now you can treat the magnetic field that there's more perturbation to that. Now, okay, you have this ground state. Now you make them move. You give them some momentum. In the rest frame of the moving atom, the magnetic field gives rise to an electric field, and that polarizes it. And that's precisely the polarization you have here. Okay? In this language, the vorticity is simply charge density. Okay? And then you compute the interaction, you get precisely this. So then why is, of course, these are particles. These E plus E minus can annihilate, and can annihilate into photons, and the photons there correspond precisely to the compressional modes in this duality, okay? Because the hydrodynamic mode, the photon of a superfluid, is dual to the, there's this duality between scalar and gauge field in 2 plus 1, right? So that would be that. So the annihilation of E plus E minus would be annihilation into this longitudinal mode. The only reason why I have not written this example is because these are atoms, in addition to this interaction with dipole, that are certainly the thing that dominates when they cross a long distance. In the S wave, there is also hard scattering. These are atoms. So there is also an interaction like phi dagger to the fourth, phi dagger phi square, which here is not there. And so this is what, but other than that, this is precisely realizing it. But maybe that's indicative that the symmetry that preserves this in physical situation cannot be realized. Yeah. I'm still confused by that. I don't know. Anyway, now I decided I want to go back and understand better real fluids. And maybe if you have 10 minutes, I'd be happy to chat and ask you.
So I actually have to go, but let's thank Riccardo and people who want to stick around.